In the previous example, we saw that we employed the open loop frequency response for performing our controller design. This is true in general. We also saw in previous modules that we use the open loop frequency response for analysis, in particular for looking at stability margins. Phase margin and gain margin are both found from the open loop frequency response plot. An exception to this, a property where instead of using the open loop, so for most things in this course we'll use the open loop frequency response, but one exception is called bandwidth, and it uses the closed loop frequency response. In particular, it's a measure of the system's closed loop speed of response. Previously, we had used the gain crossover frequency, which we found from the open loop frequency response, to measure the system's speed of response, and these two are related. Bandwidth is defined as the frequency at which the closed loop magnitude plot drops -3 decibels below the DC magnitude. In a similar way to why we use gain crossover frequency, we can see that bandwidth is a measure of speed of response because it captures the frequency at which the system starts to attenuate an input. In other words, it captures the frequency at which the system is no longer able to keep up with the input. Bandwidth in general is a common property that's used even outside of control systems. Within control systems, generally the DC magnitude of a closed loop system will be 0 dBs. We put in some input, we want the output to match the input, so we want it to have a scaling of 1 or a magnitude of 0 decibels. In other situations, for example, looking at an amplifier or whatever, it's not necessarily desired that the magnitude be 0 dBs. It might be, 100 gain amplifier or something. And so there we wish to know at which point is the amplifier no longer able to keep up, where its output is no longer able to maintain that 100 gain. We won't talk about bandwidth too much in this class, but I thought we would introduce it because it's such a prevalent property. At this point, I'd now like to compare our frequency response approach to analysis and design to the previous types of analysis and design we've been employing. In particular, time response analysis and the use of pole placement controller design, or the root locus for placing the closed loop poles. And so an advantage of this frequency response approach is, one, that it's a richer source of information than, say, a system step response. So it captures the system's response to inputs of a whole range of frequencies, all the way from a steady state input to very fast changing inputs. Whereas a step response explicitly shows the response only to a single input, though it does give some indication of how it might respond to other inputs. Furthermore, the frequency response tells us a lot more than just the poles do. So for example, if we just looked at the poles of a transfer function, that wouldn't tell us anything about steady state behavior, about the DC gain, whereas a frequency response plot does. So placing the poles all by itself is not enough to achieve a certain steady state requirement, but designing using a frequency response plot does enable us to do that. Furthermore, frequency response plots settle ambiguities from the root locus. So the root locus shows us the closed loop pole locations, so it doesn't even necessarily show us what the closed loop zeros are. So it's hard to see the effect. With the root locus, it's also hard to tell the contribution of different poles if there isn't a dominant 1 or 2 poles. So if you had 4 poles that were in the same basic range of speed of response, it would be hard to know the contribution of each. It would also be hard to know the contribution of a pole if it's near a 0. So we understand this concept of a pole zero cancellation and how they reduce the effect of one another, but how much do they reduce the effect? that you can't really see from the root locus, but you can see it from the frequency response. And I'll try and exemplify that as we go through more examples. The frequency response approach to experimental derivation is also advantageous because you can see the effect of higher order poles. With the step response, you kind of just see the effect of the dominant poles. So you can see the effect of non-dominant poles, you can see the effect of zeros, and you can see the pole zero cancellations. So every time there's a pole, every time there's a zero, you can see exactly how the magnitude changes, how the phase changes, and in turn you see the effect on DC gain, gain crossover frequency, phase margin, all of these things that tell us about a system's time response. The advantage of a time response approach or a pole placement approach is that it gives us results specifically in the time domain, which is ultimately what we want. In particular, if we have a canonical system, then we know precisely what the time response will look like based on a placement of the poles or based on an analysis of the transfer function. Whereas with a frequency response approach, often we're sort of dealing with a qualitative relationship between what we observe with the frequency response and what it means in terms of the system's time response. So far in this course, we've primarily been concerned with achieving the least amount of error possible. If we look at two different controllers, or we try and design a controller, we try to achieve a certain level of error, either steady state error or a certain transient performance which indicates how quickly we drive down the error. So, the transient sort of tells us what the immediate error is, and the steady state tells us what the error is eventually. Things like settling time tells us how fast we drive down the error. Peak time tells us how quickly we get, to our peak. There are, however, other considerations besides just how much error does the system achieve and how quickly does it get there. For example, we might be concerned with how much control effort is required, how much force or torque needs to be applied by our controller, and that has implications for cost and efficiency. Also, we may be concerned with the robustness of the system, robustness to undesired inputs or to uncertainty in our system. In the particular case of automotive applications, some things that we might be concerned with are emissions, driver comfort, driver safety, sort of the safety of our components, of our system. And so these are all what I would sort of classify as sort of more advanced topics dealing with these. But at this point we'll go ahead and discuss them at least at a qualitative level because they are so important, and we can use a lot of the tools that we've learned to sort of understand at least qualitatively some of these aspects with regard to our systems. Ultimately, we would like to find the best controller we can, which we will define as the controller being optimal. And so what defines the best controller depends on your specific goals. You sort of have to define a measure of what is best in terms of a balance of these different competing goals. Minimizing error, minimizing how much control is used, making the system as robust as it can be. This is another thing that we will talk about sort of more at a qualitative level. Okay. So first let's discuss control effort. Large control effort often means more cost in terms of the implementation and operation of a controller. Specifically, it often means more power or fuel is required. If your engine needs to generate more torque, it may take more fuel. If your motor needs to generate more torque, it may require more electricity. And so that fuel, that electricity costs money in a sense. And so requiring more control effort means that the operation of that controller costs more money. If we require a large peak control effort, then that means we also need a larger actuator, a larger engine, a larger motor, which also corresponds to higher cost. A very basic way to sort of indicate how much control effort is required is to look at the speed of response. So if we are able to get away with a slower response, then oftentimes that means that we'll require less control effort. If we have to get there very fast, then we need a big force, we need a big effort. If we can get there slowly, then it requires less force, less effort.